Okay, so I want to start off by asking everybody a question. Who really, really loves testing? That's a higher proportion than usual, but still way less than half. So, testing isn't terribly popular. Lots of people generally see it as more of a chore than a pleasure. Why is that? What's hard about it? Well, suppose you're developing tests for some software that has maybe n features. Then you're going to write, what, 3 or 4 tests per feature, something like that? That sounds okay. That's a linear amount of work. But we all know you won't find all the bugs by doing that, because some of the bugs only appear when you use 2 features together. Okay, suppose you're going to try and test for all of those. How many test cases do you need to write? A quadratic number. Okay. But you know what? You won't find all the bugs doing that either, because some bugs only appear, a bit rare perhaps, but some only appear when you use 3 features together. If you want to test for all of those bugs, you've got to do a Quviq amount of work. And this is starting to sound really like a lot of work that we don't want to do. And let me just, the very worst of all is race conditions, which by definition are interactions between different features, and what's more, don't even appear every time you run a test. So these are the reasons why testing is hard, right? You can never write enough tests. So when should you stop? What's the answer? Don't write tests. Generate them. So I've been doing this for quite a few years now with a test generation tool called QuickCheck, which dates back to 1999, 15 years, when Koen Klassen and I came up with the first version in Haskell. And then in 2006, Thomas and I founded Quviq, and we've been working with an Erlang version since then. We've made lots and lots of extensions, and we found lots and lots of very entertaining bugs. But I'm not going to mostly talk about that today. I'm going to give you a little example just to introduce what QuickCheck does, if you're not familiar with it. And I'm going to take some code that works with binary trees. It's just a simple example that we're all familiar with. So let's suppose I implement ordered binary trees, and a tree might be a leaf over on the left, or a node over on the right, with a left subtree, an element in the node, and a right subtree. Then here's a couple of functions that I might want to define on binary trees. So first of all, toList will convert a tree to the list of values in it. So a leaf, empty list, a node, we convert the left subtree and the right subtree and combine them. And member is supposed to test whether or not an element appears in a tree. Well, if the tree is a leaf, then the answer is false. Otherwise, if x equals y, it's true. If x is less than y, we look in the right subtree. If it's greater than, we look in the left, and so on. So there's the code that I'm going to test. And when we test this code with QuickCheck, we'll do it by defining a property of the code. And here's a property of the member function. It's an Erlang function definition, and what does it say? It says that, well, for all x and t that are generated like this, so x is a natural number, t is a tree, then this condition should be true. So in other words, the member function on trees should return the same result as the member function on lists if we convert the tree to its list of elements. The member function on trees should behave like the member function on lists. So we'll take the lists as a kind of model of correct behavior. Okay, let me run some tests. So here I have an Erlang shell. Let me just compile my trees code. And then I can run QuickCheck and give it that property, what's it called, as an argument. And, oh, QuickCheck will generate random tests, and then in the end, it seems that a test failed, and QuickCheck, first of all, displays a random test. Here it is, so there's a tree. It's got 3 nodes, and the test failed for this tree. And then it will shrink the test case and report a minimal failing test. So this test case is the smallest one that fails. And we can see that it has 2 nodes. So shrinking has removed an irrelevant node from the test case. Let's run it a few more times. There we are. In that case, shrinking didn't really do much. There we shrank from 3 nodes to 2 nodes, and so on. There's a bigger one. So as you can see, this process of shrinking ends up with a simpler test case that we can debug. OK, can we see what's wrong? Well, here, x is 0, and this is my tree. So I'm trying to test whether 0 is a member of this tree that contains both 0 and 1, and the member function is returning false. Of course, it should return true. So something's wrong. I need to fix the bug. OK, and that's the wrong shell. I'm going to fix the bug like this. I'm going to copy treesfixed.url to trees.url. Yes, let's overwrite. Recompile. And now my tests pass. OK, so I've given many talks of this sort before, and I've more or less done this without the copying, perhaps, and I've argued that this kind of shrunk test case makes it very easy to debug the code, because you have a very small example that shows you what's gone wrong. But now, OK, my code is working, but oh, what was that example again? So I've debugged my code. Okay. We like to think of this shrinking process, which you saw working there, as extracting the signal from the noise of random tests. Random tests contain a lot of junk, a lot of irrelevant rubbish, a lot of noise. That's their purpose. The shrinking process reduces the test down to a minimal example that you can't remove anything from without making the test pass. That's the signal, which is quite easy to debug. So shrinking is invaluable for understanding what went wrong in a test. But now we've lost that example. Now, of course, I could have thought about this in advance, and I could have saved my example for reuse. I might want to preserve it and build up a regression suite of tests, perhaps. And in reality, we don't always find failing tests as quickly as in my little demo. In reality, it may have taken a long time to find that failing test. And in that case, we don't want to lose it. We want to save it. So there's several reasons why we might want to save failing tests so we can rerun them. And that's what I'm talking about today, a continuous integration tool that we're building that is based on QuickCheck. So let me do the same thing again, but this time using the continuous integration tool. So to do this, I will find it in my browser. Here it is. So when we go to the corresponding web page, it has a web interface, and there's some stuff there. And then I can register a project. So let me add my project, which is in users, John, desktop, trees. There we go. The project has not yet been built. Can you read that? OK, let's queue a build. OK, and now in the background, I hope it's compiling my code. Yes. Oh, and now we can see that my project contains one module, trees, and it's colored red, and that indicates that there's a failing test in there. If I click on trees, I can open that up, and I can see that there are 2 properties in this module. 2, I only showed you one before. The ordered property just says that all the trees I generate as test data are ordered. Otherwise, they wouldn't be good tests. But the member property is the interesting one. And if I click on this now, you can see that I actually have 3 examples listed. And let's make this slightly larger still. In fact, there's a caret here. If I click on that, we can see that there's one example that the CI system has found that it doesn't bother to show us. because it's very similar to the one above. So why is this one similar to this one? Well, it's the same, except that where this one has a 1, this one has a 2. So let's not bother with the similar examples. So we can see now a number of examples. We can see the coverage of the code. If I look at the coverage of trees.earl, we have 100% coverage. Excellent. And if we look at it, we quite like this coverage display. Up here, we've got a scroll bar. And you can see the shades of green show you how much each part of the code has been executed. And if I hover the mouse over this stuff, we can see, let's see, here's my ordered property. That's been executed 100 times. Here's prop member. That was called 13 times. You can see the darker shade shows 202 calls of that code inside the property, 13 calls of the generators. And we can even hover over the clauses of member and see that here 42 calls of when x was less than y, 64 when they were equal, 57 when they were greater. So we can visualize the degree of execution of each part of the code. Okay, but let's go back to these examples. We can also take an example. Let's look at this first one, for example. So here we're trying to test whether 0 is a member of this tree. If I click on the example ID, then I can look at the coverage of the example. Well, this example only covers 45% of the code. Let's have a look at it. Okay, so we didn't cover this code, which is generating test data, because when we run one example, we don't need to generate anything. We didn't cover prop ordered, because we were testing prop member. Look at the code for member. Look at that. Now here, the colors are maybe the wrong way round. Green shows we executed something in this test, and red shows we didn't. But this is a failed test. So the bug is somewhere in what we executed. So green means danger, and red means safe. Okay, so if we look at the green code here, well, we tested whether something was a member of a leaf. Okay, that's not very interesting. But here, when I'm testing if X was a member of a node, this is the case we landed in. If X is less than Y, we tested if X was a member of the right subtree. But that's wrong, isn't it? I should have tested if it was a member of the left subtree. Okay, now I know what to fix. Let me go back to, if I can figure out how, my editor. Okay, so here, really edit the buffer? No. Yes. Thank you. I'm glad you're awake. Okay, so I should look in the left subtree, of course. Save anyway. Yes, do it. Okay. What? You think so? Let's find out. Okay, so now I need to, because this CI tool is working with the repositories, I need to commit those changes. There we are, that's that. Go back to the interface and queue another build.
Can you set it up so that it will queue builds automatically?
At this point, no, you have to click that button. Okay, oh look, something still failed. Let's have a look. The same property failed. Oh, but now one of my tests at least passed. Oh, that's progress. That was the one that I was looking at. But we can see there are other tests that failed. So let me look at the coverage of one of those. Well, that wasn't a good one to look at. I covered all of the code. That's a surprise. Maybe I should look at one of the other ones. No? Okay, not quite sure why that happened. I've done something wrong. Well, in that case, let's use Costas's intuition that I might need to change the other one as well. Okay. And if I do the same thing, not that window.
Also, if you really want to use this one with any term, you really have to use equal, colon, equal.
Equal, colon, equal. Yes, I know, I'm a bit naughty that way. And let's queue another build. And this time, they all passed. And we can see that the test cases are still there, so that should I ever introduce those bugs again, then the test is still run and they would still be caught. Okay. The code is buggy. Okay, but I'm not testing for that particular kind of bug. Because that's not the point of the example. Yes, I have. No, I've chosen my test data and I've chosen to use NAT as the test data. And then I won't discover problems caused by floating point. Because it makes a good example. Yes, so if I had used term, I would also have to be very careful about the choice of terms so that I sometimes generated the same term twice. Otherwise, it wouldn't be interesting. And with NAT, I don't need to worry about that. So it makes a very simple example to present. And also, it's often a good way of testing. But let me go on and continue with my slides. So what have we seen? We've seen that as we run tests this way, then we collect the test cases and we build up a regression test suite automatically. And that's nice, partly because it just lets you see progress in terms of tests that did fail and now pass. Otherwise, one of the frustrating things about using QuickCheck is you find a bug, you fix it, you run QuickCheck, it's still buggy. But you have actually fixed some of your tests, and that becomes more visible with this framework. And the other thing, as I said earlier, is that if there are test cases which were very hard to generate, now they're automatically saved so that you don't have to manually save the things. And the other thing that I hope you've seen is that by presenting this coverage information in a lot of depth, so we can see coverage by all of your tests, coverage by a single property, coverage by a single example, then that not only makes it easy to see at a glance what's being tested, it lets you see what the distribution of tests was. If you see one branch was tested only a few times and another branch many times, you can ask yourself why. And it even helps to localize bugs. When you run an example, you see the code, just the code that that example covered, then that's where the bug must be. Now then, I want to show you another example. I'm going to do the same kind of testing, but this time of some stateful code. And I'm going to use the process registry, which has already appeared in several talks in this session. I'm going to test really just two operations, the register function and the unregister function. But in order to generate tests for these functions, I'm going to need to create PIDs as test data. So my test cases are also going to contain calls to spawn. So what's different about register and unregister from the simple tree example? Well, these functions change the state of the registry, and we have to reflect that in the tests that we write. I just want to emphasize that I'm not expecting to find bugs in the Erlang process registry. It's been around for a long time, and it's very heavily tested. So it's been used a lot. I'm not expecting to find any problems. So what I'm going to do instead is I'm going to reverse engineer some of the preconditions on those calls. I'm going to generate tests in which register and unregister don't raise exceptions. Now, maybe you all know exactly when they raise exceptions and when they don't. But if you don't know, then this is a way to find out. How do we test this kind of thing? Well, we use a state machine model. So we generate test cases that do sequences of API calls. In order to model what's happening inside the system, we pick a model state and we define state transitions for each function. And then we write postconditions that compare the result from the actual call to what the model says should happen. And then what shrinking is going to do when we get a failing test is just discard some of the commands that are not relevant to the failure. How can I model the registry state? I'm going to do it with an Erlang record that looks like this, in which I'll track a list of PIDs that have been spawned, so they're available as test data for registering. I'm going to add to that list by calling spawn, and I'm going to track which names have been registered and what PIDs they've been registered with. So that part of the model is going to be changed by register and unregister. I want to show you what the model looks like. Here's the specification of the register function. So we can give a precondition. Here, the precondition for register says there must be a PID for you to register. Obviously, if there are no PIDs, you can't call register. The next function says, here's how to generate the arguments for register. You need a random name and a random PID, an element of the PIDs in the state, in the model. Here's how you do a call of register, or how you execute a call of register in a test case. You just call Erlang register with the same parameters. And here's what register does to the model state. When we call register, the next state is just the one before, with a list of registered processes updated by adding the name and PID to the end. So this is how we specify operations. And the reason that all of these functions have names beginning with register is that QuickCheck picks those up and interprets them as a precondition, argument generator, state transition function, and so on.
Why did you write the last thing there? Besides being wrong, it's quadratic.
You are asking why I append name and PID to the end of the list there. In some cases, it leads to better shrinking. And it doesn't matter, because there's never going to be more than maybe a dozen things in that list. It doesn't matter. It really doesn't matter. It's much more important that test cases shrink well than, you know, a few microseconds when you execute them. Okay, so let me demo this. So I will need to select a different project. Okay, I haven't added this one yet, so let me add it. Users, John, desktop, registry. Queue a build. This takes slightly longer, not because it's quadratic costis. Okay, and indeed my property failed. So let's have a look. If I click on the property, we can see there is actually two tests that failed. In the first one here, then I called unregister, and it raised an exception, a bad arg exception. Okay, why might unregister A raise an exception? Well, A wasn't registered, of course. So that's one problem. But if I scroll down here, there's another one. What happened here? I spawned a process, and then I registered it with the name A, that returned true, and then I registered it again with the name A, and that raised an exception. Why did that one raise an exception? I can't do that. I used the same name twice. So we can see that there are two ways in which I can violate the precondition here, and I found them both in one run. So let me go back to my editor, and I have to switch to the other project. Okay, so here we have the code. And what I will do here is I'll add a precondition for register that says it must not be the case that the name is in the list of regs. And correspondingly for unregister, another precondition, when you unregister a name, it must be the case that the name is in the list of regs. Actually, there's a precondition up here on the state. Okay, different number of arguments. This one says, don't even think about doing register unless you have some PIDs. And this one says, don't do this particular call of register unless the name is absent from the list. Okay, now I'm sure I'm going to forget to do this sooner or later, but come back. No? Okay. Nothing to commit because I'm in the wrong folder. There we are. That's committed that. And now if I run my test, remember I've got 2 failed examples. Let's queue a build. Oh, it still fails. Look, prop registry fails. But look, my first 2 examples pass now. The test case is excluded by my precondition. But there's more cases that fail. Well, let's have a look at this one, for example. What happened here? Can you read this? Okay. So, I spawned a PID. I registered it with the name A. That worked. I registered it with the name B. And I got a bad arg exception. Ah. You can't register the same name twice. But more than that, you can't register the same PID twice. And my precondition doesn't say that yet. Okay, let's fix that. Here's my editor. I'm going to need a stricter precondition here. And also, it must not be true that PID is there as the second element of something in state.regs. Okay, let's see how many of those cases this fixes. No, I don't need it for unregister. So this should do. Okay, git commit, queue a build. Oh, it still doesn't work. But I fixed almost all of my bugs. So this is progress. However, here at the bottom, we have a property that is still, an example that still fails. And actually, we've got 3 similar ones. So let's have a look at the failed one. What are we doing? Oh, I'm spawning a process. I'm registering it. Actually, let me just look at this is a bit easier to read. I'm spawning a process. I'm registering it under the name B. I'm unregistering it. That worked. I'm unregistering it again. That raised a bad arg. Well, of course it raised a bad arg. Well, why was I unregistering it again? Unregister says, doesn't it, that I shouldn't call unregister unless it's in the model. Well, let's just look at the similar examples. Okay, what's this? Oh, it's the same, except the name was C. What's this? The name was D. Okay, can anybody guess what this one's going to be? That one's A. So let's look at the code, which I can do just looking at the coverage information. This is actually the code of the spec. Unregister removes something from the registry. But where is the next state function? It's not there. Ha-ha. Now we know what the problem is. So let me just add an unregister next. Okay, state. When you unregister a name, the effect of that is to replace the list of registered processes with this key delete. the name. Oops. That should work, shouldn't it? Git commit. Back to the CI. Do another build. All my tests are green. That's great. And let me look at the coverage. Again. OK. I just want to show you one more thing. Here's my property. It says, for all command sequences, first of all, we have to unregister all the names to get into a known state. Then, if we run the commands and check the commands, everything should pass. But look at this. Check commands would run 100 times. I ran 100 tests. Look at that list comprehension. That unregister was run 400 times. What does that tell me? It tells me on average, well, in fact, in every case, the list of names had 4 elements. So you can see that the body here in the list comprehension was run more times than the surrounding code, and that tells you how long the lists were on average. In this case, that's obvious because there are 4 names in my list. You've seen them. A, B, C, and D. But in other cases, it's really interesting to be able to look and see, this list comprehension, on average, there were 0.2 elements in the list or whatever. And this is the kind of information that the cover tool you get with Erlang just doesn't show you. So it's a much more refined level of coverage information. OK. I think that is enough demo. OK. So you've seen the state machine models. We find them a very convenient way to specify the intended behavior of stateful systems. Even in much larger cases, we write the specifications just with a collection of small function definitions like those ones I showed you. This is a small example, but it's a realistic example. And it doesn't really get much harder than that. QuickCheck CI now gathers a variety of interesting test cases. It groups them sensibly. I think you would probably be quite glad not to see all those similar examples that I showed you in great detail if you were working in practice. And the little exercise I've gone through here, it's more realistic than you might think. And you might think, reverse engineering preconditions. Who needs to do that? Who needs to reverse engineer the specification of our code? We know that. So you may think, we found in practice the specification of the code that we're starting from is never correct. Why should it be? It's a complex document that has not been tested. Of course specifications are wrong. So testing in practice involves partly reverse engineering what the spec really should be, and at the same time finding and correcting bugs in the code. So it's only the latter part that you haven't seen in this demo. You might be forgiven for wondering, well, will this really scale up? Over the last few years, we've been doing it for Volvo Cars, and we've been testing part of the AutoSAR basic software. So in a modern car, there are 50 to 100 processors, and they run a lot of code. There's one estimate that a modern car contains 100 million lines of code. Why? But still, they do. All of those processors run some basic software that enables them to talk to each other. And here's a diagram that shows this stuff. You'll recognize an Ethernet stack. Yes? Processors in cars have Ethernet stacks on them. The CAN bus is a communication bus that's used very heavily in cars. LIN and FlexRay are other communication protocols. The COM services up the top, they provide routing between various networks. The diagnostic cluster, it's a very fancy name for the software that remembers that a cylinder misfired and tells your service station when you take your car in for a service. So this is a picture of the software. Each of these boxes is a component which is specified by 100 pages of PDF. So each of the black boxes, that contains software whose specification will be many hundreds of pages. And Volvo Cars wanted to be sure that when they bought components, the software that they contained actually conformed to the spec. And luckily, there is a standard which all the suppliers follow. So that guarantees, of course, that they're all consistent. Well, in practice, putting together a car from systems from different suppliers with software from different suppliers is a nightmare. You put it together, you can't even boot the car. So that's why Volvo Cars were interested in having very extensive testing. We read 3,000 pages of PDF specifications. We wrote 20,000 lines of QuickCheck code. It's not a whole lot for 3,000 pages of specs, and it's 20,000 lines of quite simple code, like the code I showed you. We could use that to test 1 million lines of C from 6 different suppliers. And we found more than 200 problems, of which more than 100 were problems in the standard that the suppliers were supposed to follow. So we think this is something that we're very, very proud of. And many of these problems we've fed back into the standardization process. So a lot of those problems are fixed now. We were able to compare our test code to existing test code for some of these modules, and we found our test code was 10 times shorter. So does the approach scale up? Yes, it does. Would you like to try it out? Go to this URL, Hans SV, that's example proj on GitHub. Shall we do it now? Where is my browser? Come back, oh browser. All is forgiven. Here it is. This is an example project that we put up. And look, it's QuickCheck tests, passed. Click on that. And you come to the system that I showed you, except instead of running locally on my laptop, it's running on QuickCheckCI.com. So if you'd like to try this out, take your project, register it at QuickCheckCI.com, and we will run your tests for you. And somewhere here, I have my picture. Done that.
Yeah, but can I run it locally?
So right now, no, it's not in the latest release yet.
Okay.
But of course, our plan is to release it so that it can be run locally at customer sites. And talk to us about what you would like from a local version. Good. So we have focused here on doing the best we can, knowing that we're running QuickCheck properties. Hence, we're collecting the test cases that are generating this kind of stuff. And that's our focus at the moment, rather than trying to integrate with, for example, Travis CI. I suppose we might think about that later, but for now, we're just trying to do the best job we can with QuickCheck properties.
What happens with failed examples when API changes functions?
Oh, yeah, sure. I didn't demonstrate that. It would have taken me a little bit longer. But if I go back to, which one is a local one? This one. Okay, so here are the examples for the registry property. And you can see on the right here that some of them they're all marked as active. Now, what typically happens is either you change your API or you change your property, or for one reason or another, your example becomes no longer relevant. And then you don't want it sitting there, turning your tests red the whole time. So you just inactivate it. And now they won't run in future builds, unless, of course, you come back to this build and mark them active again. So you can disable examples that you no longer want. It's necessary to be able to do that. Simon. Do you think Wrangler could help to inactivate irrelevant counterexamples? Now, if only we had an EU project together, Simon. we might be able to do some work on that. Costas.
Basic question. First of all, I mean, obviously I like what QuickCheck is doing, right? Even closing. But the basic question from a scientific point of view is how do you know that you have enough tests? And in the case of, even in your simple cases here, in your examples, in the case of the tree, you can never find out the bug because of the way you have chosen to write generators. Proper will find the generator. This will find the bug because it has the. But this particular one, in the case of the registry, you don't find any bug where there is a race condition between the process being alive and trying to register in while it has been dead. Because you have a race condition, you spawn a process, and now it has done its thing, it died, and now you try to register it, and this crashes. So the point I'm trying to make is that always, you are always going to be missing some part that you haven't tested. So how do you have any ideas how we can help there?
So I have a very scientific answer to the question, have you tested enough? No. And it's very hard to say more than that, isn't it? So we're not aiming with this work, or in general, we're not really aiming to answer that question. Rather, we're aiming to help, test as well as you can. Will it be enough? Not always. When we write properties, we're deciding which tests we want to run. And there may be some bugs that cannot be revealed by those tests. And, that's... I didn't hear that, Costas.
You cannot even find all the preconditions and post-conditions. So here you have a false, the point I'm trying to make is that here you have a false, you give to programmers a false sense of, okay, now you found the preconditions and post-conditions of the register and register, the process register. And you have it. This is a very important one.
And which one do you have in mind? I'm missing at least two. Oh, sure. Yes, so if I were to talk about this example for much longer, I would add killing processes as an operation appearing in tests. And then we could extend the preconditions to capture the behavior of the registry when processes die. So I could do that. It's not in these tests, because these tests don't include process death. But, when we define QuickCheck properties, we choose a set of tests that we want to run. And you still have to use your skill and judgment in making that choice. If you were to try to choose every possible call, every possible event, you might have a very wide range of possible tests, but your chances of running any interesting ones that would detect real bugs would become very low. So, there's a design choice for tests as well. All we're trying to do is make those choices easy to make. So that instead of designing one test case at a time, you can design a whole set of test cases at a time. But you still have to think about what set of test cases you want. I think we've reached the end of my slot. So if there are no more questions, maybe our chairman will thank me.